Hello everyone, welcome to the volume and surface area introduction. This is going to lead us into chapter 12. For right now, we're just doing a broad overview. I think that's going to be a really helpful thing for us to do at first before we get into the nitty-gritty parts of this chapter. So the chapter 12 overview for geometry here. By the time we're done, you should know what surface area is, volume, what a rectangular prism is or looks like, a cylinder, and specifically a right cylinder, a pyramid, specifically a regular pyramid, a cone, specifically a right cone, sphere, and what slant height and lateral area, what all those things are by the time we're done with this. So I want you to start by creating, you can title this like you see up here, Volume and Surface Area Introduction for Chapter 12, but in your space, in your space for, there we go, in the note area, I want you to make a table that looks kind of like this, and it's going to be, this will be the titles of each column, the column headings right here, and I want you to make 5 separate boxes going down, 5 different rows, as well as the title heading row. Okay, and so in each row, take a moment to do that, pause if you need to take a moment to do that. Make this as wide as you can so we have as much space as possible to put our work in here and to put our pictures and whatnot in here. So let's get started on this and see what we have here. So in this first column, I want this to be both the description and the picture. So we're going to put a description and the picture in this one. So what is it and what's it look like? Here is going to be the surface area formula for that particular object. Surface area, sometimes we call that SA for surface area. And then volume, sometimes we call that V, makes sense for volume. So let's start off with probably the easiest one. This is going to be a rectangular prism. Rectangular prism. And why don't I put all this stuff in, you don't have to use a different color for this, but I just wanted to stand out so you know what the picture is and where I'm going from there. So let's make this blue instead for here. So rectangular prism, what's it look like? You do the best you can right now freehand. I'm just going to freehand these things as best I can. Make yourself a box. So I want you to start off by drawing a rectangle. Some people find that they are most successful by drawing another rectangle right behind that, a congruent one, and then connecting all the lines like that. Some people like doing that better. I kind of like just going back like this, the same length. If you do that second rectangle behind the first, make sure you're definitely using pencil so that you can erase some things. But these go back at the same angle as best as you can. Connect those. That's the part you can see. And then with dashed lines, this would come down here, this would come out here, this would come here. So I'm going to put a little point where those would intersect, and then I'm going to connect that point to all the vertices that are in the back or behind, the things you can't see. I'm going to connect it like that. Those are hidden lines representing now this 3-dimensional objects on a 2-dimensional piece of paper. And so this I want to label with an L for length, with a W for width, and H for height. And then I'm going to put a capital B right here and another capital B right here. We'll see what that stands for in just a moment. So a rectangular prism looks something like this. It's a box, okay? That's the other name for this, but the less technical name, rectangular prism, is what we'll use most of the time. But just think box. If you've learned it that way before, that's what we're thinking again here. And what is the surface area? What's it going to equal? The surface area, in this case, with a rectangular prism, is going to equal 2b, and we'll say what all these things stand for in a moment, plus p times h. That's the big thing you need to remember for surface area of a rectangular prism. Now, why does this work? What does surface area mean, first of all? Well, surface area is exactly what it sounds like. It's the area of the surface. So if you were to find the area of all the surfaces that are showing on this, you would have the area of the right side and the left side, the top and the bottom, and the front here and the back here. We'd have 6 different areas to add together. We can find that by taking 2 times b. b is just the area of the bases. So I'm saying this is my base and this is my base, and I can add that to the perimeter. That would be L plus W plus L plus W. If I'm taking the perimeter, the whole thing at once, multiplying that by the height, it's going to give me all 4 of these, the right, the back, the left, and the front, all 4 at once. The 2b gives me the top and the bottom all at once. And so this is a quicker way than to find the area of each of the 6 faces separately. It's a quicker way to do that. I think this works better. All right, so B, this stands for, right here, do this in a different color for me. This is the area of the base. P stands for perimeter. And H, that stands for height. And all those things, H at least and B are labeled here. The perimeter is just going to be L plus W plus L plus W all the way around. The volume of a prism, this I'm pretty darn sure you've heard of before. L times W times H, length times width times height. So please, in a different color, let's label those things. This is length. W is width. And the H, that is your height. Okay, so go back and review that as needed, but that hopefully will make sense. Volume being this times this times this. It's a 3-dimensional measurement, and this will always be in units cubed. A surface area is always in units squared. So units squared for surface area, units cubed for volume. Next up, we've got a right cylinder. And I say a right cylinder because finding the surface area and volume of a non-right cylinder, that's a little different than finding just a right cylinder. So right just means straight up and down. I want you to draw kind of a half circle or a half ellipse. We're trying to draw this on a 2-dimensional piece of paper as best you can to represent a 3-dimensional object. So it kind of looks like this. Pretend like you're looking at a soup can from an angle, okay? And drawing that as best you can. This part you couldn't see, but there would be this other base right here. This is going to be B for base. This is your radius. That's a little R right there, and this is your height. So for a right cylinder, the surface area, what's the area of the whole surface? Again, hopefully, as I explain through things here, these will start to intuitively make sense. You won't have to memorize these formulas because you'll know exactly how to derive them or where they come from. So what's the area of the surface? Just like here, we had 2 bases, and we could take the perimeter would give you all the way around times the height would give you all 4 of the faces laterally, which reminds me, I wanted to say one more thing about this up here, that these 2 together, the P and the H together, is your lateral area. So let's write that down underneath here. Lateral area is just the P times H part. And sometimes you'll see lateral area referred to as LA. So lateral area, P times H. So here's the surface area. It's the same thing. It's the same idea. You have 2 bases, a base right here and a base right here, the bottom and the top of the cylinder. So you still have another 2 times B, but in this case, your B, we can write it like this. Let's write it like this first, and then I'll show you the other way to write it after that. Your B is going to be that, and then think of P being the perimeter, but a perimeter of a circle is circumference instead. So this is going to be C for circumference times height. Now the way you're going to see it in the book, and the way I think is better to think of it as, is 2 pi r squared. B is the same as pi r squared. and your circumference is 2 pi r. That's what circumference is. That's a formula we should know from before this lesson, and we've got that right here. So this right here, the 2 pi r, this is your base, the area of the base. This 2 pi r part here is your circumference. Abbreviate that like that, and this part is your height. And just like before, there was a lateral area. I'll abbreviate that with an LA now that I've said what LA stands for right there. It's not Los Angeles, it is lateral area. The lateral area would be the area of the part kind of around the shape, not on the top and the bottom. Just like here, lateral area was around the shape. Think lateral, think around down here. We've got what's around the shape. That would be the circumference all the way around from here, wrapping all the way around to here. That's where that circumference part comes from, multiplied by the height. That would give you, like if you were to take the label off of a soup can, you'd cut that label, you'd peel it off, and the length of that going all the way around would be the length of the circumference, and we'd multiply that by the height. And so this would be, your LA part would be the 2 pi r h. Okay, so C stands for circumference, capital B for base, but base, think pi r squared, circumference, think 2 pi r. So this is the way I really want you to remember this one. This might help you remember why it is, but this is the one that's really important to remember. So let's circle that in our pencil. That's the one that I really want you to think about. And your volume, think of it that same way. It's your base here times the height. So we can still think of it as capital B times h, but the better way to think of the capital B when you're talking about cylinders, you're talking about circles here. This is a pi r squared for your B times the h. And again, let's put some things in a different color down here. This is your base, and this is your height. So it's really no different. Here the length times the width, over here was your base. Here the base is the pi r squared part since it's a circle instead. So this is the key one to remember here. But if you think of base times height, you'll think of this hopefully, because you know the base is a circle. There's three more that I want to hit here. The next one I want to touch on is a right pyramid. Right, just think of going straight up and down. Just like right triangles kind of go straight up and down, perpendicular. Right pyramids, right cylinders, right cones is another one we'll get to. Those things go straight up and down. This one's a little tricky to draw, but I want you to try to think of a square base for right now. Pyramids could have different bases. You could have hexagonal pyramids or pentagonal pyramids or even triangular pyramids or a lot of other types of pyramids. But I want you to draw these two, so they're about the same length as best you can. From here to about here, we're going to make a line there and there, and then connect those. So think of Egypt, think of the pyramids there, and hopefully that'll help you. And then here at the same angle you went back here, I want you to do that same angle here. Imagine that going back, and we'll do this with the dashed lines because you can't actually see these things. These are hidden behind what we already have. And then this way, going this way, it would look like that. And so that's not too bad, I feel like. In a different color, I want you to draw this extra triangle in here. So if you go straight down, you should end up close to the middle of that square. I'm not going to get super technical right now or super picky on how your drawings look, but try to do the best you can, of course. And then this triangle right here should be a right triangle, so make a little box right there for me. We're going to call this lowercase l, We'll see what that stands for in a second. This right here in a different color still, this is lowercase h. That's a height of that. This L actually stands for something called the slant height. And then back to your normal color, I'm going to put a capital B where the base is. Just like before, that's the area of the base. That's what the capital B refers to. So this is still surface area. The surface area of this, we'll think of the area of the surface again. So you've got this bottom part, and in this case you've got these 1, 2, 3, 4 lateral faces going around, going laterally. You've got those 4 things. So you have a base, that's the surface area of the bottom, plus, well, what would the lateral area be? Well, if you think of these, they're always going to be triangles, because this vertex where they meet up at the top, that's what a pyramid is. We'll define that more technically later, but they all meet up at this common vertex at the top. You're always going to have these triangles being formed. Triangles, remember, are just 1/2 base times height. And so what would the base of this be? Well, we don't know, but we could find these would all be the same. If it's a right pyramid, these are always going to be the same lengths all the way around here. And so from there, I actually meant to, I'm sorry. This should be regular pyramid. I meant to say regular instead of right. It should be right, but it should also be regular. So a regular pyramid, that's where they're going to be the same all the way around, because this, and this, you'd have the congruent sides there. This would be a square in this case. You could have a regular pentagon, a regular triangle, hexagon, heptagon, octagon, and so on and so forth. You could have any of those things here, but this all the way around would be the perimeter, would be capital P. So if you know the perimeter, you can take 1/2 of the perimeter, multiply it by this part. This would be your height individually for each triangle. But if you do it all as a group, you can find the area of those 4 triangles all at once by taking 1/2 of the whole perimeter, multiplying that by this slant height part, this lowercase l part. So this is 1/2 times the perimeter times the slant height. And let's label those things in our different color. This is the area of the base again. The capital P here stands for perimeter of the base. And this is called slant height. I'm not exactly sure why they used a lowercase l for slant height, but that's what they used. I'm using a cursive L here so it doesn't look like a 1. The slant height is just like it sounds. It's the height, but it's not the straight up and down height. It's the height on a slant. Sometimes you're going to have to use the Pythagorean Theorem. You can see a right triangle right there. You can use the Pythagorean Theorem to figure out that slant height. So if you knew this part, or if you knew a whole length, then you could find half of that and get this length and find the slant height based on something like that. The volume of a regular pyramid is going to be, it's the same, or it's based on the formula that you had for a box, this base times height right there. It's the same idea, but you can actually, we're not going to prove this right now, but you can actually fill up 3 cubes, I guess it would be in this case. A cube is just a special type of rectangular prism, but you could fill up 3 cubes with the amount of water that the same regular pyramid could hold if it had the same base as a cube. So this would be 1/3 capital B times H. And again, let's label what's what here. This is the area of the base again. And this capital, or this lowercase h, still the height. So pretty neat that always works like that. I don't think that's intuitive at all. It would be 1/3 every time. And then finally we've got a couple more here. We've got our right cone. Just want to introduce all these things. We're not going to do any examples right now. We are just going to be looking at what the formulas are later on. We're going to use our notes here, if you're a member of my class, to do some examples, some together, some you'll try on your own. So here's a right cone. It kind of looks like a regular pyramid in the sense that it's all meeting at this vertex, but the difference here is the base is a circle instead of some sort of regular polygon. The base here is a circle. And let's draw in red again. Let's make this part go straight down. You're going to have the center point of your base right there. This would be at a right angle. Again, you have a slant height right here. This part, put that in red or whatever color you are using. And this will be the h, the height, and the radius. And the slant height is right there. So again, I see Pythagorean Theorem going on right here because I see a right triangle. I can always use the Pythagorean Theorem to figure things out where I have right triangles. So I have the surface area is going to equal, think of it as your base plus, and then this part takes a bit to prove. We're not going to prove that this is true or why this is true right now, but it's this pi r times the slant height. And again, I think the better way to think of a base when you have circles is to consider it as, and let's put a capital B here in the normal color, but to consider it as pi r squared. And then this part will be your pi r L. Okay, so this is surface area. This is the way that it's best to remember this one. That's the best formula to use for that. Pi r squared, this whole part here is the base, the area of the base. And then this pi r L, this is the lateral area part, the part around there. So lateral area, in this case, the LA part is going to equal pi r L. Up here I forgot to mention that the lateral area here was this part. The non-base parts is the lateral area part. And so it's 1/2 perimeter times the slant height. And then finally for the volume of a right cone, the volume is going to equal, it's the same sort of thing. This 1/3 idea ends up working for cones as well. So you have 1/3 of the base times the height. But again, when you have these circular bases, better to think of volume as, in terms of the capital B, replace that with pi r squared. So pi r squared is what your capital B is, and that times the height. So let's circle this one. This is the better one, I think, to use, but this is the one where you can derive this from. So think of it the same way as you thought of pyramids. This value right here, though, this pi r squared part, again, that's the area of the base. And this part, that's your height again. And finally, a sphere. For right now, these are the 5 we're talking about. Sphere, right cone, regular pyramid, right cylinder, and a rectangular prism, or sometimes we'll call that a box for simplicity. So a sphere, I want you three-dimensionally, we're trying to make this look three-dimensional at least. I want you to draw a circle, but then draw this kind of semicircle, ellipse, half ellipse thing going on here, and then hidden line back there. Find the center point of that sphere. Think of this as maybe like a basketball, soccer ball, something like that. And it's got a certain radius. We're going to call that R. What is the surface area of a sphere? This takes quite a bit to derive. I remember learning this, deriving this, proving this myself in calculus for the first time. I was pretty amazed at how amazing calculus is, to be able to figure out that the surface area of a figure like this, it's actually equal to 4 times pi times r squared. It's 4 bases. Whatever the area of that circle is, if you took 4 of those circles and you took the area it took to paint one of these circles here, and you multiply that by 4, that would be the area needed, or the paint needed to paint the entire area surface-wise around the sphere. Pretty neat that that always works. So 4 pi r squared, that's the big thing to remember here. And the volume of a sphere, it always works out that it's 4/3 pi r cubed. Again, that is beyond the scope of this geometry class that you are likely in right now. Proving why that's true, we're not going to get into that, but it always works. You can use calculus to prove both of these things. Again, pretty amazing, I think, that always works that way. Love math because there's always a right answer, and there's almost always a way to prove something or disprove something. There are some theorems out there that have yet to be proven or disproved. Some of those problems are worth $1 million actually if you solve them, literally. There's some millennium problems that they're called. If you can solve them and the math community agrees with your work, you can go get yourself $1 million. There's a reason they haven't been solved yet, though, by anybody, because they're very, very hard problems. But I hope that helps you with a brief introduction here to Chapter 12, what you're going to see in terms of the formulas for not only prism cylinders here, but also pyramids, cones, and spheres, the surface area formulas, and the volume formulas. And again, we're going to be practicing these with different numbers, getting a lot of repetitions, and getting a lot of practice before we're taking the test on these, and hopefully we'll do really well come test time and know how to actually find and apply this to real life problems, how to find the surface area and volume of these shapes, and again to apply it most importantly to real life phenomenon and problems. I'm going to stop talking for now, though. I think I have worn out my welcome here. I feel like I'm just going on and on. So farewell, see you guys later. Hope that helped. Rewind, pause, reflect as necessary.